Okay, I guess we can get started. You guys have any questions before we begin with the notes and things? Okay, so last class we were talking about population, and I mentioned India a few times. You know, China usually gets most of the attention when we talk about population and places on Earth where population problems exist, but as we discussed last class, India has about the same population as China. And you don't hear all that much about it. And I think you should. India is an amazing place. It's one of the most beautiful places I've ever been, and it's one of the ugliest places I've ever been. And sometimes the two can be mere feet apart from one another. So I got to visit the Taj Mahal a few years ago. Seriously, it's one of the most beautiful things that humans have ever created. I really didn't even want to go. It's just a building, you know, but this picture just doesn't do it justice. It's absolutely stunning how beautiful it is. And when you go to the markets, you see the same thing. You just see lots of beautiful food, beautiful people, beautiful dress, beautiful everything. But then you can go literally, you know, a half a block away, I don't know what that is, and then see something like this, which is just garbage that can't be picked up because the infrastructure isn't advanced enough for that great of a population. You know, you've got 1.2 to 3 billion people, and they all want the things you want. They consume a lot, and when you consume a lot, you also have a lot of waste, and they don't have the infrastructure to remove the waste. So you end up with things that look like this, or I don't know what's going on with this, like this. We talked about the fact that garbage doesn't always get picked up, but yet people are making garbage every day. And you know, if you have a business or a home, what do you do with that garbage? So to alleviate it, what happens a lot of times is that they will just bring the garbage out to the front of the building, along the road, and just light it on fire at the end of the day. And then sadly what happens is the animals then go into the burned areas and look for any scraps of food that may not have burned properly. So as you're driving down the road, you'll see cows and dogs and all manner of animal in these burn sites. And you can see here they just extend all the way up and down the roads. You know, it's just a matter of trying to get rid of the garbage, because if they didn't burn it, the problems with pests would be even worse. You imagine all the food that gets tossed out and then animals digging around in it, making a huge mess. You know, it can, so this is kind of the best they have. So this is one of the oddest things I've ever seen. This is a parking lot near one of the palaces in the northern part of India. The palace is just gorgeous. It's unbelievable. But when you walk around the palace and go into all the places, all of the corners of all the hallways and outdoor spaces smell like urine, because there's no public restrooms, there's nowhere to go to the bathroom, and there's so many people that, you know, you're trying to find anywhere that you can to have some privacy to pee. So people pee in the corners of everything, and as you walk through, every time you come to a corner, it just, the pee smell is just overwhelming. And here you're looking at this gorgeous building, and all you can smell is urine. So what they tried to do to keep people from peeing in every corner was they would put these urinals out in the parking lots and try to get people to use them. And me, being curious, it's like, okay, when you pee in that thing, where does the pee actually go? So I had to walk up to this and walk behind and look, and you pee in this thing and it goes down that little pipe and it literally just goes out the back and it just sits in the parking lot. So I mean, I don't know really what it accomplishes, but I guess it's, you know, trying to keep people from peeing on every nice thing in some of the nicer areas. And this was just wild to me. So you got this guy peeing in the parking lot, you got monkeys up on the rails, a homeless guy over in the corner. It's just the weirdest place I've ever been. And I talked about the fact that the population is about 1.2 billion, but about 800 million don't have access to bathrooms. They don't have toilets to go in. So you go where you go, and this is a field where they're growing crops. And when you gotta go, you gotta go, and they're doing their nice social distancing thing there, but you know, that's what you see when you go through the rural areas of India. people have to go to the bathroom outside, and they pretty much go everywhere because there's so many people. And then this is a little waterway in Delhi. You can see the garbage is mounted up so high. There's actually 2 dogs that are standing on the garbage that's floating in the river. That's how thick the garbage is there. And that's actually not that unusual of a sight. So this is what happens when population grows faster than the government can provide infrastructure for things like garbage removal. You end up with garbage accumulating at just a horrific rate. And people get sick from this stuff. I mean, it cuts down on their economic viability because it obviously hurts tourism. People don't want to see this sort of thing, so they avoid these kind of areas. But there's a lot of sickness that results from this. Diarrhea rates are off the chart in India. So it's a place where population has really sort of reared its ugly head, because even though there's some real prosperous areas, they simply can't keep up to the growing population. We're adding people faster than they can solve the problems in this particular area. So, you know, whenever you see travel photos, you don't get to see this. These are my travel photos. I love taking pictures of the flip side of what you might normally see when you go somewhere. Okay, you guys have any questions? All right, I want to finish up with the population thing. We kind of blew through it at the end, and my sound cut out for the people at home, so I wanted to just spend a minute and kind of sum up. So, to sort of set this up again, remember that usually when you hear population discussed, it's kind of in a negative light, you know, similar to what we were just talking about. We're adding 1 billion people every 10 years right now. Those people need resources. The fear is that a growing population is going to use resources up faster than we're going to be able to get them to the people. And back in the early 1980s, this is when the awareness of population really first came on the scene nationwide. And a guy named Paul Ehrlich, who I have mentioned here a couple times, he's an ecologist. He wrote a book called The Population Bomb, which, to summarize, really outlined all the problems that were going to occur over the next 40 or 50 years because of human population. Basically, we're going to eat and consume ourselves out of planet Earth if this doesn't change, and we really need to do something about population control on the planet. Well, that was countered by an economist named Julian Simon, who said, you know, this is just wrong. Your whole premise is wrong about population. Because I look at this from an economic standpoint, supply, demand, things like that, and I'm simply not seeing the doom and gloom that all of these biologists and ecologists are projecting. And he basically said, you know, if we really are having problems with population, if we add 1 billion people and they start consuming too much, what's going to happen to the price of things if things start getting scarce but people want them? Prices are going to go up. He goes, I will bet you that in 10 years, the prices for just about everything that humans use, metals, food, burlap, oil, coal, natural gas, those prices aren't going to go up. They're actually going to go down, which means there's more available to humans 10 years from now, even though we're going to add 1 billion people who are going to use things. Obviously, those extra 1 billion people are going to use stuff up, but it's going to be counteracted by human ingenuity. We're going to be able to produce more food on an acre of land. We're going to be able to dig more stuff out of the ground. We're going to be using less stuff to do the same things because we get more efficient. And you know what? Even if we start to run out of something, let's say we start to run out of copper for wires and transmissions. Well, if that gets expensive, then human ingenuity will come around and find an invention, a solution that will use something else. And it'll be cheaper. So what you're not counting on in this argument that human population is bad is you're discounting human ingenuity that comes with more people. So he said, I'll bet you that in 10 years the prices of everything will go down. And the population bomb dude, Paul Ehrlich, said, yeah, I'll take that bet. And so how did it play out? Well, it doesn't matter sort of what time period you go through, whether it's the 1980s, 1990s, 2000s, it almost always works out that the boomsters win, that prices actually do go down. Because we are a real smart, ingenious species. We solve problems. And Ehrlich was a man of his word, and he sent Simon a check in 1990 for $1,000. And in fact, every resource that Ehrlich had picked that he thought would go up in price actually went down over that 10-year period. Now, why did these prices fall? Well, for a lot of reasons we just mentioned. Basically, we got better at doing things over that 10 years. Computers reduce labor cost. In fact, it's being suggested by some that as we go on in the future, automation, computers are going to do so much work for us that there might not be enough work for all humans to do. You know, everybody comes to college, oh, I want to get a job someday. But if we keep getting more and more efficient as a species, we might have machines be doing all of our work for us. Then how do we make a living? And some people have started to think about that. And in fact, Andrew Yang, who was a Democratic presidential candidate, has been thinking a lot about it. And he said, you know, at some point, the government might just have to pay people to stay alive. You know, they're not going to be able to work because there's not going to be enough work for everybody to do. So maybe at some point, we're going to have some sort of universal paychecks coming from the government. And you can imagine how that's going to go over in parts of this country. But that might be a reality down the road, is that what happens when we get so good at doing work that computers and machines do it all for us? How do we make a living then? You know, we're obviously not to that point now. But what about 50, 60 years from now? How does this play out over time? So it's something that people are talking about. Yeah?
I was going to say somebody's got to fix all the machines and computers away.
So there will always be jobs, right? But is there going to be enough jobs for, you know, in 50 years, we might have 13 billion people. Is there going to be enough work for all of these people? Or is everybody going to be able to make a living if we're so efficient at things? You know, the world's going to change a lot in the future, and that's one way where it might. I don't know how it's going to play out, but it's something that people are starting to talk about. Said before, you know, when things get so expensive because they do run out, then humans just switch over to something else. We are going to see this with fossil fuels. You're going to see this with oil and gas probably in your lifetime. We are eventually going to run out of petroleum. Petroleum is not something that we can just go deeper into the earth and get. It's a resource that exists only up near the Earth's surface. When we get down too deep, it gets hot, and that basically ruins a lot of petroleum products. So at some point, we're going to run out of petroleum, natural gas. What's going to happen as we do start running out? What will happen to the price of those things? It'll go up, right? Right now, coal, oil, natural gas, they're cheap. The things we talk about as renewables, they're more expensive. Things like solar, wind, whatever. But, you know, as the price of fossil fuels creeps up, pretty soon some people are going to say, hey, you know, they're sort of comparable now. I'm going to invest my money, instead of investing in fossil fuels where I was making a lot of money in the past, I'm going to start investing in some of these alternatives. And when you invest in the alternatives, then those companies have money to start making things better and getting more resourceful with their money. We've been extracting coal, oil, and gas out of the ground for 100 years. We're really good at it. It's pretty cheap to do. At some point, we'll invest in, I don't know if it's solar or tidal or whatever, but when that happens, we'll get more efficient at that, and that will bring that price down. So what are you going to use at that point? You're going to use one of these renewables. So at some point during your lifetime, I think, you're going to see that switch over. And that's just because, again, of human ingenuity. When we do run scarce, we switch to something that'll ultimately be cheaper. We talked about how fiber optics has already done this in the past. It replaced expensive copper wires back in the 70s and 80s. And now we use microwaves for a lot of our phone transmissions. We don't even have wires. Things like when I was born, cans were made of steel and tin. And then sometime in the 70s and 80s, they switched over to aluminum. It's cheaper to make. Ultimately, things got less expensive because we improved our process for aluminum extraction. So, I asked you at the end of last class, how many of you are still doomsters? How many of you think growing population is still not a good thing? Or do you think we should just add 1 billion people every 10 years? It's not so simple, right? It's good points and bad points to it. And I think you can argue to some degree that at this point in time, humans have done a pretty decent job keeping up with population-induced problems. Sure, we have places like India where, we just cannot build infrastructure fast enough for the growing population. But we know how to do it. Just a matter of will at some point. Will we actually do it? Simon had this quote after he won the bet with Ehrlich. He said, both Jayhawks and humans eat chickens. But the more Jayhawks you have, the less chickens you have. Because they eat the things indiscriminately. The more humans you have, though, the more chickens you have. Because we're really good at creating resources. We can grow chickens in these massive farms. We have more chickens on the planet now than we ever have, even though we have more people. We're good at doing a lot of these things. But I used to ask this in all my classes. I said, can you think of a problem that might pop up that population is going to make worse, that we're not going to be able to solve in time before it exacts a real toll on humankind? And, sometimes I'd get answers. Most people didn't really have an answer, but the answer that I was looking for is, what about a pandemic? And, I don't think anybody really gave it much of a thought. I've been talking about pandemics for like 30 years. It's like the one thing that we might not be able to solve quick enough that could spread through humans so fast where it could, wipe out a huge part of our population. I mean, with this coronavirus thing, the death rate is low overall. Still kind of scary, When you're talking about 1 out of every 100 that gets it dying, I don't really want to play with those odds. But what if we had a pandemic where the death rate was 50%? Half of everybody who contracted it died. Or could be more. I mean, we don't know what could happen in the future. But having all these people on the planet is going to make it worse, because that's how these pandemics spread, is from person to person to person. And when you have so many people close together, that makes it really easy for these things to spread, doesn't it? Right now, India is the worst place on the planet for coronavirus. They're about to surpass us. And we shouldn't be this bad. We're just being dumb. India just has so many people that it's going to spread quick. So, some final thoughts on population and we'll move on. Is growing population good? Sure, there's good aspects to it. With more people, more ideas. Some of these ideas really make our lives better and easier. Is growing population bad? Sure, it's got some bad aspects too, especially when it comes to things like pandemics. Trying to provide infrastructure for clean water, energy, garbage removal. Those are things usually that are not discussed in great detail when you talk about population. Everybody talks about resources. They don't talk as much about infrastructure. Providing garbage removal. When you have lots of resources, you have lots of garbage. So you got to have the flip side. You have to have that garbage removal. So if you ask me personally, I'm not a doomster or a boomster. I'm a little bit of both. I know population growth has some good aspects, It also has some terrible aspects. And here's where it goes for me. So this whole premise that Simon put out that, if we add 1 billion people, we add 1 billion people's worth of ideas. I don't think we have to add 1 billion people to get a lot more new ideas. Because if you look around the world, a lot of people, probably most people are on the planet, are in situations where even if they had a great idea, it doesn't freaking matter. Because they have no way to capitalize on their good idea. If you're some 14-year-old girl in rural China who doesn't have access to school, you might be the next Einstein brain-wise. But if you don't have a avenue, a mechanism to go to school or go out in the workforce and make your idea become a reality, then what good is it? So to me, it seems like rather than add another 1 billion people, maybe we should be putting our efforts into bringing up folks that are in situations where they can't capitalize on their ideas because they live in impoverished areas, or they're a woman who lives in a culture where women's ideas don't matter as much as guys' ideas. There's a lot of that. Or racial problems. You got places where one race dominates over the other, and folks that are on the lower end of that, they don't always have a mechanism to make their ideas come to fruition. So if we can enable all people to contribute, we don't have to add 1 billion people to get better ideas. Those ideas are out there, they're just not being capitalized on. So anyway, I wanted you to think differently about population than just the doom and gloom. There are some good aspects to it, but there are some bad aspects to it as well. So I'll just leave you with this. Few things in life are absolute. We're in this political season right now where everybody wants a meme or a soundbite for a solution to a problem, but a lot of our problems are complex. One of the issues that might come up in this presidential election is, should we be drilling for oil and gas in protected places like the Arctic National Wildlife Refuge or national parks? Should we be doing that? And yeah, you get politicians and they love to have their quickie little sound bites and things, but these are not simple answers at all. They're complex. They have good aspects and bad aspects. If you want to keep drilling out of national parks, there are some really good things about that idea. But there are some unintended consequences to that as well that oftentimes don't get talked about. And if it was simple, we'd already be doing this stuff. So my point is, use your brain, use your education, question everything you hear, even if it's coming from your professor. You guys should not be taking everything I say as gold. You should challenge me. You should argue with me. You can tell me I'm full of shit. I do not mind. I want to see that from you. I don't care how you vote. I don't. What I care is that you've thought really hard about the issues at hand and where the various candidates, not just president, but all up and down these ballots, where they stand. As long as you come to an informed decision, that's all anybody can ask of us as citizens. So don't take the quick, easy soundbite way. Stay off social media. Okay, so these first couple weeks in this class, what I want to do is I want to give everybody the background needed to understand some of the more complex topics that are going to come up. So this class, and probably a little into the next class, we're going to go through some real basic chemistry, physics, and geology. I want everybody to have the same background. Now my guess is that all of you have probably encountered most of these topics at some point in your academic career. For some of you, this is going to be boring rehash. I know all this crap. For some of you, it's like, I've never seen most of this before. For most of you, though, what I'm going to guess is like, you're going to look at it, it's like, yep, saw it, forgot it. So this is a reminder session more than anything. So these are the basic concepts that we're going to use in all of the chapters that are going to come after. So after this basic chapter that we're going to go through, we're going to transition into water. We're going to spend about a month talking about water. We'll talk about the oceans. We'll talk about rivers. We'll talk about groundwater. We'll talk about how humans use water, how humans abuse water. And then we'll move into energy. And we'll do the same sort of thing. We'll look at the science, and then we'll look at sort of the interactions with humans. And that'll take up most of the semester, believe it or not, and energy and water. That's really what this course is going to come down to. And you're going to see most of our topics in earth science are related to those two things. Okay, so let's just get into these background basics. So one of the most fundamental concepts in physics is heat and temperature. Heat is a form of energy, and we're going to talk about this a lot when we actually discuss energy. And temperature is a measurement of how much heat is in a system. Now for you, I'm going to keep this really simple. What I need you guys to remember is that heat really just, it does one thing. It makes atoms vibrate more quickly. That's what atoms do. They vibrate. You know, if it's really cold, there's not much heat, they vibrate really slow. And if you add heat, they start vibrating faster and faster and faster. So if you take something like a solid chunk of ice, all of those water molecules, they're kind of stuck in place. It's cold, right? Ice is pretty cold. So they wiggle, they move around, but they can't move around enough to break away from their neighbors. So let's crank up the heat. When you crank up the heat, what do those atoms and molecules do? They vibrate faster. And eventually they'll vibrate fast enough that they'll start breaking the bonds with their neighbors. At that point, your solid ice breaks down into liquid water, and it melts. And then if you keep adding heat, what happens to that water? It gets warmer, gets warmer, gets warmer. Pretty soon you have so much heat that those water molecules are moving so quick in your liquid that they start flying off from the liquid and become a vapor or steam. So a liquid can become a gas as the temperature increases. That's just one manifestation of increasing the heat and making atoms and molecules vibrate more quickly. Now in geology, we talk about the surface of the earth. Are you guys under pressure right now? I see one or two of you doing this. Do you feel like you're getting squished? I don't feel squished up here, but there's pressure on all of us right now. What's that pressure from? You're actually being squished by something.
Atmosphere?
Yeah, we have this air mass that sits on top of the earth, right? And gravity is pulling it down on top of us. We're just used to it. You know, but if you went to the moon, you'd be under a lot less pressure, and you'd actually feel it. And in fact, when you go up in elevation here on Earth, if you drive up into the mountains, there is less air over the top of you when you're up high. So you have less pressure on you. Do you notice it sometimes, the pressure changing as you go up into the mountains? How do you notice? What do you notice? Your ears, right? Your ears are probably the most sensitive part of your body when it comes to pressure. So your ears can pick it up. So your ears might notice those small changes in pressure. And then the real way that you get pressure in geology is to go into the earth. That's where the real pressure is. And I always tell people, you know, what we can do is we can dig a hole that's 3 or 4 feet deep, can throw one of you in it, can bury you with dirt, and gravity's going to pull that 3 or 4 feet of dirt down on top of you, and you're going to feel the pressure. Now, if I threw you in a 10-foot deep hole and filled up with dirt, you'd feel a lot more pressure. If you go down 4 or 5 miles, you'd feel tremendous pressure. And it's all because of gravity pulling stuff above you down on top of you. And sometimes this manifests itself as changes in how things behave. We can take gases, and if we squish them enough, they can become liquid. We have things like liquefied natural gas. Natural gas that's under so much pressure that it's in liquid form. It's much easier to transport that way. Okay, gravity. I've mentioned gravity a couple of times. When I ask people, what is gravity? Most people will say something like, oh, it's the thing that pulls us down on Earth. It's the thing that keeps us on the ground. And that's one way to look at it. Nothing wrong with that definition. But it's actually more general than that. Gravity's amazing. It's a universal force. It's everywhere. You can't go anywhere in the universe and not be influenced by gravity, to some degree. Even out in the deep recesses of space, there's gravity out there. Gravity occurs wherever you have mass, wherever you have stuff. Do you have mass? Each of you has mass, right? I have mass, you have mass. Table has mass. Your pencil has mass. Everything that you can see, touch, feel, smell has mass. Gravity is the force of attraction between anything that has mass. Okay? So you have mass, I have mass. You have mass, I have mass. You two both have mass. Are you attracted to each other? You both have mass, right? So yeah, so there is actually a tendency for you two to like come together. And there's a tendency for me to go to you and you to go to everybody else in this room, right? Does the ceiling have mass? Are you attracted to the ceiling? Yeah. Yeah, there is a pull by the ceiling on you. So how come you're not stuck to the ceiling? Or stuck to me? Or stuck to the blackboard? Or my computer? So the amount of mass, though, influences the amount of gravity. What is the most massive thing around you? The Earth, right? So that force of gravity sort of swamps out all these smaller attractions that might be working on you. So force of attraction between things that have mass, that is gravity. So the more massive two bodies are, the greater the gravitational attraction going to be. So look to your left, look to your right. You are going to be more attracted to the more massive person that's near you. But you're not going to actually move physically towards that person because you're more attracted to that big old Earth body that's below you. But I have a question for you. What's more massive, the Earth or the Sun? Sun's way more massive than the Earth, thousands of times more massive. So how come you're all not zooming out through space, barreling directly at the Sun? Because it's far away and there's a distance component to gravity as well. The farther the two bodies are apart, the smaller the attraction. So even though the Sun is much more massive than the Earth, given that it's millions of miles away, its gravitational effect is going to be much smaller than the Earth that's right adjacent to you. Now you can look at this as, for those of you a little more mathematically inclined, there's actually a definition for gravity. I don't care if you remember this, but it simply shows that gravity is proportional to two masses. So the greater the masses, the greater the gravity. But you see on the bottom of that equation, a little d, that's for distance. So the greater the distance, the smaller the gravity. And distance has a huge effect because it's squared in our equation here. So gravity dies off really quick as things get farther away. So you don't have to, like I said, you don't have to remember this. I'm not going to ask you to spit this definition out. It's just another way of saying what's above it. The more massive bodies are in question, the greater the gravity. It's counteracted then by the distance between the objects. So when you put all this together for the Earth and the Sun, it just means that the Earth has a lot more gravity on you. So what if you're bigger? What if you're a big person, big massive person, and you're here on Earth? Earth is going to be more attracted to you than a small person, right? So the Earth is going to pull down a more massive person stronger. How do you weigh yourself? You stand on something, right? And the Earth pulls you down. And the more it pulls you down, the more you weigh, right? So the more mass you have, the greater the Earth's attraction to you, the stronger the pull is going to be, the more you're going to offset a scale when you stand on it. So what if we went to Mars? Mars is a planet that's about the third the size of the Earth. A lot less mass than the Earth. What's its gravity going to be on you if you suddenly were transported there? It could be a lot less, right? So you're going to weigh a lot less on Mars. In fact, you're going to weigh about 1/10 of what you do here. So I'm going to weigh around 15 to 20 pounds. I'm so dunking a basketball on Mars. Okay, any questions on this so far? All right, again, all basics, stuff you've probably heard before. All right, this next one is one that confuses people, okay? Because it's really similar to gravity in some ways, but there are some important differences. And that is magnetism. All right, magnetism is the force of attraction or repulsion between things that have a charge or things that have poles. So I have this little box here. You guys see this? We're going to pretend this is a magnet, okay? Most of you have probably played with magnets before, right? Now, if I let go of this magnet, what's going to happen to it? It's going to fall, right? All right. Why did it fall? You said gravity, but it's a magnet. So what is how is magnetism and gravity different? So we said this is a magnet, right? I let go of it, it falls. But you said it falls because of gravity.
Because the desk isn't a magnet.
Desk isn't a magnet. What if the floor was a magnet? And I let go. It's going to fall, right? Why is it falling then? Does a magnet have a gravitational attraction? Always does. Why? It has mass, right? It's an object just like anything else. But because it has poles, it can also have magnetic attractions. Let's say the ceiling was a magnet, okay? And then this is a magnet. And if I let go, what are three things that could happen to it? Okay, if it falls down, what does that tell you? Gravity's stronger than the magnetic attraction pulling it upward, right? Or it could go up, right? Which means that the magnetic attraction is greater than the gravitational attraction. Or you said, what was the third option? It just hovers, right? Which means what? It means it's being pulled up by magnetism as much as it's being pulled down by gravity. which they can do in a lab. It's actually pretty cool. And in fact, if you go, anybody been to Japan? I've been on the bullet train in Japan. It's awesome. It actually sort of floats on a magnetic layer. It's levitated by magnetism. And you can go 300-400 miles an hour on that thing. It's perfectly smooth. I love the bullet train. It's one of the coolest things in the world. But yeah, so we can actually use this for different technologies. So it works a lot like gravity, and that's why people get confused. The greater the charges, the greater the magnetic force. Some magnets are just ridiculously powerful. Some magnets are so strong that if you have a metal plate in your body, it can actually rip it right out of you, which has happened, which is not cool. But it can happen. It's not common, but it is possible. And just like gravity, there's a distance thing. The farther you're away from a magnet, the smaller that magnetic influence is going to be. We're going to come back to magnetism in a few minutes, because the Earth is a magnet as well, isn't it? The Earth is a big magnet. So not only does the Earth have a strong gravitational attraction, the Earth is also a magnet. Okay, this next property is something that crops up a lot in geology. Buoyancy. And that's spelled correctly. It's probably the most misspelled word I get in my classes. People flip around the U and the O, but this is how you spell buoyancy. Buoyancy is simple. It simply means that less dense materials rise to the top of a system. Can you guys give me an example of buoyancy, something that you've seen in your house, out in nature? Okay, it's a little more complicated. So a rubber ducky sitting on top of a water. What about a boat sitting on the water? Boat's made of metal, right? If you put metal in water, where does it usually go? Straight to the bottom. Because of the shape of the boat, it displaces water. So you've got something a little different going on there. What if you put oil and water together? What tends to happen? Oil rises to the top, right? Because oil is slightly less dense than water. What about ice and liquid water? Ice floats, right? Ice is a little less dense than liquid water, so it floats. So there's a couple of examples that you guys know. But I'll complicate it a little bit more. It also exists not only with liquids, like with oil and water, but can also exist with gases. Cold air, because the molecules aren't moving as fast, they're not vibrating as much. That means those molecules can pack together a little more tightly and be more dense. So cold air tends to sink. Warm air tends to rise. That's where we get our wind. That's where our winds come from. The sun heats up the atmosphere. That warm atmosphere rises. As you go up higher, what happens to air? It tends to cool off, and then it sinks. So you get these circulations that go on in our atmosphere, and that's the origin of our wind. But believe it or not, it also works with rocks. And it works with rocks in the Earth's crust. So what you see up here is a little diagram of what we call a subduction zone. It's a place on Earth where we have two of the Earth's crustal plates coming together. Okay, and kind of hard to see. I'm a little tethered up here, but I think I can do it. Way on the left there, that's a section of ocean crust. Okay, so that is rock at the bottom of our ocean. And if you look, it says 3 grams per cubic centimeter. That is the most common density for ocean rocks. Now that ocean plate on the left is moving from left to right. On the right here, we have a continental rock mass, continental crust. You can see that the density of that continental crust is 2.5 grams per cubic centimeter. It's not as dense as the ocean crust. It's about 20% less dense. So if you have two rocks that are colliding together, and one's denser, what's that denser rock going to do when they collide? It's going to go down, right? So it slips beneath. And that's why you have the subduction zone. You have the denser plate that's sliding beneath the less dense plate. And we have lots of places on Earth where this is occurring. It occurs in the Pacific Northwest, Northern California, Oregon, Washington. It occurs all along the west coast of South America, where the Andes are forming. It occurs over on the other side of the Pacific, where we have Japan, Philippines. What if two rock masses collided and they were the same density? Would there be any tendency for either one to slip beneath the other? No, so what they tend to do is they sort of pile up. They just smash into one another, and the crust gets super, super thick. And that's actually happening where India is slamming into Asia. So you've got India, which is a continental rock mass, slamming into Asia, which is a continental rock mass. What do we have between the border of India and Asia? Anybody know? I think I heard somebody say it. That's where the Himalayan mountains are. The tallest mountains on Earth where we have the thickest crust. And that's because those rocks that are colliding are the same density. Neither one wants to slip beneath the other, so they just sort of pile up and get super thick. That's where the crust is the thickest here on Earth. So that's what this is trying to show right here. So you have India, which is sliding to the right in this diagram, crushing into Asia, which is going to the left in this diagram. Neither plate wants to give way to the other one, so they just sort of buckle and get really, really thick. And that's why we have such a tall mountain range. It's where Mount Everest is, 29,028 feet. Lots of peaks over 20,000 feet. And it's all because you have two rocks of the same density slamming into one another. Okay, I'd like you to just take a minute and do a little exercise for me. I want you to draw what the inside of the Earth looks like, based on what you know. So just imagine that you could cut the Earth in half like an orange. What do you think the inside of the Earth looks like? So go ahead and label your diagram. I'd like you to put a volcano on there somewhere and where the magma's coming from to feed that volcano. And then put a tectonic plate on your diagram as well. So I'll give you just a couple minutes to do this. And I'm not going to ask you to hand this in or anything, so. And I'll just warn you, your diagram's wrong. And if I draw it, my diagram's wrong. Maybe my diagram would be a little less wrong, I hope. maybe it would be. I hope I've learned some things through my years as a geologist that you guys might not know, but maybe I don't. But all our diagrams are going to be wrong. Okay, looks like fewer of you are drawing. So I want you to take a look at your diagram. That diagram came from your brain, right? Somehow you had some stuff in your brain that you knew about the Earth. Where did you learn about the Earth? Where did your ideas come from? I'm sort of glancing out there and I see most of you drew a nice round circle, right? And then you have some stuff going on inside, correct? Okay, I can tell you that the distance from where you're sitting right now to the center of the Earth is about 3,600 miles. That's about the same distance as going completely across the United States. The distance from Boston to LA. And you know how far humans have actually physically gone into the Earth? The deepest that a human has actually plunged down into the Earth? Anybody know? About 2 miles. 2 miles. That wouldn't even get you out of downtown LA, would it? So directly, we don't know much about the Earth. We haven't been very far down. I've been one of the deepest people into the Earth. There is a mine in South Dakota called the Homestake Gold Mine. It's the deepest mine in North America and one of the deepest mines in the world. And it's about 2 miles deep. And I went down there about 25 years ago. It took about 15 minutes to get to the bottom by a real fast-moving elevator. 15 minutes in an elevator, just going down, going down. And as you go down, it gets hotter, and it gets hotter, and it gets really stinking hot. And at the bottom, it was, I think, 123 degrees. And no air moving at all. It's just nasty. Just nasty. And yet, I was only 2 miles down, and the crust of the Earth at that point is 30 miles deep. No human has ever been to the mantle of the Earth. And yet, I'm guessing a lot of you guys drew the Earth's mantle. And yet, no humans have ever been there. And certainly nobody's been to the core of the Earth either. But all of you probably drew the Earth's mantle, core, or some sort of combination of things, right? So we know something about the inside of the Earth indirectly. And we'll talk a little about that as we go forward. So, you know, where did your information come from? Maybe you had a geology or earth science class in 8th grade. Maybe you watched movies. There's some really bad geology movies out there, like The Core and Armageddon. Those things are horrible. And they have lots of misconceptions going on with them. So what we'll try to do in this class is bring you towards a more scientifically valid view of the Earth than what you might get. Or maybe you had Magic School Bus. That's actually halfway decent, you know? So we'll get into that. You can get on the internet and find all sorts of really terrible ideas for what's going on inside the Earth. I found this one, got heaven in the middle of the Earth. You got lots of air inside the Earth, and this idea is bad. Okay, we're going to end with this today. I'm just going to give you sort of the scientifically accepted version of what the Earth's interior looks like. And this is a real simplified version. We learn new things every year about what's going on inside the Earth. And I'll put up a diagram to go with this in a minute so that all of these different zones, you sort of have a visual to go with it. So at the deepest parts of the Earth, 3,000 to 4,000 miles down in the Earth, it's actually as hot as the surface of the sun. It's damn hot down there. You know, if it can hit 120 some degrees going down 2 miles, imagine how hot it is 3,600 miles into the Earth. It's hot, hot, hot. But, so if it's that hot, what do those atoms want to do? They want to vibrate like crazy, right? But they're also getting squished, right? Because they have 3,000 miles of rock sitting on top of them being pulled down by gravity. So at the deepest parts of the Earth, we believe that the Earth is probably made of solid nickel and iron. It's like a giant ball bearing. And just to the outside of that, a little closer to the Earth's surface, is the outer core. It's made of the exact same stuff as the inner core, but it's under a little less pressure. So those atoms can move a little more freely. They're super hot. So they are probably in a liquid state. We're going to talk about what all this actually means for us living on the surface, but these things deep down actually affect us here on the surface, and in kind of a big way. As we get a little closer to the surface yet is the biggest zone within the Earth by volume, and that's called the mantle. Now, one thing about the outer core that I will mention, it's liquid, right? Okay? But this is not where magma that comes out of our volcanoes comes from. First of all, because what comes out of our volcanoes is liquid rock, not liquid metal. Why does this material from the outer core, even though it's liquid, never get to the Earth's surface? It won't even try. Try in quotes. Why doesn't it even move up towards the Earth's surface? Something we talked about a little bit earlier, property. It's too dense. It's way more dense than everything that sits on top of it. So it doesn't rise buoyantly. It just sits down there because it's super, super dense. Liquid metal. It's not going to go anywhere. So that's not where the magma that comes out of the volcanoes originates. So right beneath our crust is the mantle. We've never been to the mantle. We've never even drilled to the mantle. I have a piece of the mantle in my office, though. I do. It's really awesome. It's made of this green mineral called olivine. If you've seen the gemstone peridot, that's the same mineral. And the mantle is full of that stuff, and I have a piece in my office. So if we've never drilled to the mantle and never physically been to the mantle, why in the hell does your geology professor have a piece of it in his office? Any idea?
Is it less dense?
That's exactly it. The rock itself isn't less dense, but that's where magma originates that comes up in our volcanoes. And in fact, the magma that comes out of the volcanoes in Hawaii originates in the mantle, and sometimes that magma will actually grab a piece of the rock from the mantle and bring it up with it. It's just a little inclusion that gets stuck. It's like a hitchhiker. The magma moves up from deep within the Earth's upper mantle, and it brings a little piece of it with it. So you can get lots of pieces of the mantle coming out of volcanoes. So even though we haven't been there, it's decided to pay us a visit up here on the surface. We can't say the same for the inner core and the outer core because it's just too dense. Those things don't move up at all. And then sitting on top of the mantle is the crust. That's what you're familiar with. The crust is actually pretty thin on the oceans, only about 7 kilometers thick. That's 4.2 miles or so. For you true Americans who've never learned your metric system, so about 4 miles thick. I mean, that'd be a good place to drill to the mantle because it's thin. Then again, you got that whole ocean sitting on top of it, which makes drilling difficult because ocean water moves. Here on the continent, especially like here in Colorado, it's about 50 kilometers thick to get down to the mantle, or about 31 miles. How deep is our deepest mine, did I say? About 2 miles. How thick is the Earth's crust on the continents? About 30 miles. So, you know, when we talk about running out of things, we're really not running out of much. The Earth is a huge place. You know that mine I talked about? They closed that mine up. There's so much gold still up there. So much gold down at the bottom of that thing. But humans can't work very well in 120 some degrees, so they would have to pump air conditioning down there to keep it an environment that people could work in. And it just became an economic reality that it would be more expensive to actually work there, pumping electricity and using all this energy, than you'd get back from the gold you dig. So we're not really limited in terms of resources because the Earth is a huge place. We're limited by our ability to go get some of this stuff. But if in the future we become a little more efficient with energy and a little more efficient with air conditioning, maybe we could go and extract gold at deeper depths. The Earth is a big place. With the exception of fossil fuels, we're really not running out of anything. We just can't go get them because we lack the technology. So I'll leave you with this. This is what we think the Earth looks like, a real simple view. So the Earth's crust is actually so thin that the outer line in that big diagram is thicker than what the crust would be proportionally. So they have this little blowout part in the upper right part of the diagram. So you can see the inner core. Solid, think of it as like a giant ball bearing. Surrounded by the liquid outer core, which is also metal, super dense. It's about 4 times denser than the mantle rock that sits above it. And then the crust is just that thin little scummy layer around the outside. Super thin in the oceans, only about 4 miles thick, 30 miles on the continent. And you can see it's about 6,400 kilometers from the surface to the center. That's about 4,000 miles. Roughly the distance across the U.S. All right, so I'm going to leave you guys with this. We'll hopefully finish up the background next class, and then we'll move on to talking about water for a month or so. If you guys have any questions coming up, on Thursday, we'll do class, but then I'm going to give you some lab materials that you can take home, okay? We'll do lab distance-wise for a couple weeks till we see how this COVID thing works out. But I'll have you pick up some maps, take them home, and then I'll put up a little video walkthrough of the lab. It should be pretty simple, okay? All right. If you have questions, come on up. If not, I will see you all on Thursday.